Well, welcome to HL Colloquium. Today we're very happy to have Dr. Greg Kopp here. And Greg is no stranger to a lot of us. He's a local, and actually he's a native Boulderite. And he completed his physics degrees at Caltech and then Stanford. And one thing he learned, he believes important part of those educations was that he will appreciate Boulder all the more. And one big reason for that is the multiple complementary solar institute in town. And after a postdoc at NSO and also a few years in the industry, and he did use the word enjoying industry, and he came back in 2000 and has been building remote sensing instruments at LASP. He's a scientist for the TSI monitors, TSI monitors on source, Glory, and the TSI sensor, TSSIS, and also the new instrument, TSI calibration instrument, TCTE, which he will talk more today.
Thanks everyone for coming too. You guys kind of get back-to-back LASP talks today, it seems like, and real complimentary ones too. Dan talked about space weather, and I'm going to talk more about what you might call space climate. So long-term changes, probably not as exciting as the space weather events, but long-term, they can have pretty big effects. Title is Solar Irradiances continued with a new mission, and just to avoid any suspense, I'll tell you immediately what the new mission is. It's the TSI Continuity Transfer Experiment. It just launched on the 19th of November, so barely over a month ago. And it's new enough that don't hold your breath, that there aren't any wonderful, neat results that I can share, but I am going to lead up to why we want this mission flying and the data that we've gotten up to this point and why we need the continuity that this is going to be providing and what it's going to be doing. This is our total solar irradiance, or TSI, climate data record, the Spaceborne part. That is the 35 years of measurements that we've gotten from space of the total output, radiant output of energy from the sun. So for you guys, especially at HAO, who understand all the neat little details and intricacies in the sun, I'm going to really dull it down a whole bunch. We're taking the entire sun, spatially and spectrally, integrating it up into one number. The only excitement is that that one number changes a little bit with time. But this is the 35-year record that we have from about a dozen different experiments, each of them in their own color here, that show how the total energy from the sun varies with time. And down here, you see the sunspot record. And you'll notice that the total amount of energy from the sun is in phase with the sunspot record. Sunspots themselves cause short-term decreases in the output of light that you get from the sun. But overall, the faculae and other activity that you have near solar maximum more than compensate for the short-term decreases that you get from the sunspots themselves. So this is the record that we have. That was the space-based record. This is the TSI climate data record that's proxy-based. So we take the 35 years of spacecraft data that we have, and then you correlate that with something like sunspots, or cosmogenic isotopes, or F10.7. And that lets you extrapolate back in time what we think the total energy from the sun has been for the last 400 years. This here only goes back 400 years because that's the sunspot record that we have. So you can see the Maunder minimum back here, and a likely decrease in total energy output from the sun over these 400 years. You can go back further in time using cosmogenic isotopes. You can correlate those changes with changes that we have in climate temperatures on the Earth via tree rings or ice core samples. So it's these long-term kind of climate records that we're really after and the sun's influence on the Earth's climate. Yes, sir. Kurt. It's based on a lot more than that. And I do have a graph coming up that will show that while I call this the, I was real tempted to actually scratch out the V here because there are several proxies. But the long-term trends shown in this one are from estimates of the open magnetic flux of the sun, and thus how those affect incoming cosmic rays that we detect from ice core samples. So this particular model is based on open flux from the sun and then long-term variations from cosmogenic isotopes. But there are a lot of other ways of putting together proxies. So it's not independent, that's right. Yeah, and everything is tied to these last 3 solar cycles, which is the only place where we've gotten real measurements. So there's a lot of uncertainty, more and more as you go back in time. But it also means that it's really important that the measurements we're getting currently had better be good, because that's what all the proxies that we're going to extrapolate backwards are going to be tied to. We can't go back and improve the measurements that give us those proxies. The only thing we can do is make better measurements right now to which we can tie proxies. So yeah, neat question, but there's a lot of assumptions that go into a long-term record like this. And the more you extrapolate back in time, the more difficult and uncertain things get. How do we use these? Judith Lean puts together nice plots, reconstruction records via regression models of temperatures. So in white up here are the last 30 years or so of globally average surface temperatures. Then what she's done is fitted those temperatures to 4 different components that you see down here. One of them is the solar cycle that I just showed you the composite from. Another is anthropogenic effects, increasing greenhouse gases, changes in water, how we're affecting with black carbon, soot over ice, how we're affecting the poles, a lot of anthropogenic effects that have overall been causing temperature increases. Here you can see volcanic aerosols. There's Pinatubo that remember Bill Livingston complaining about a whole bunch when he was trying to observe at the McMath because of how it was messing up his observations. But volcanoes can put up enough dust to block incoming sunlight, but only for a short period of time, a few years. But enough of them happen over time, and they can really cool things off. They do correspond to changes in temperature globally. El Nino Southern Oscillation, these kind of ocean atmosphere circulation patterns that change on the Earth and affect temperatures. But regressing all 4 of these components together, Judith can come up with a good fit to the global temperatures and account for something on the order of 75% of those changes just from these 4 components. But the sun is one of these critical components feeding into us being able to understand climate change on the Earth. So that's what really drives these measurements. But here you can see some of those effects. El Nino causes about a 0.2 degree increase globally, a lot higher here in the Pacific. It's characterized by warm Pacific waters. Usually heats things up a bit in North America. Pinatubo cooled things off in North America and across most of Europe and Asia here. Anthropogenic effects seem to really be targeting Europe. They are way ahead of us in terms of trying to stop things with climate change, and this might have something to do with it. And the solar cycle regionally seems to also affect Europe a bit more than it does the Northern Americas. So these are purely regression models using temperatures from different locations and fitting them to each of these 4 components to try to understand what it is that's affecting climate in different places. And she has put together a compilation of regionally how the sun does affect things by monsoons, rainfall, droughts, warming. So there are a lot of signatures or correlations between what the sun is doing and what's happening temperature-wise on the Earth there isn't a whole lot in the way of really understanding anybody being able to say, oh, if you warm the sun up, here's why. Here's a global climate model that's going to predict why different regions are affected differently. So far it's kind of at the, oh, that's a neat correlation. We want to learn more about it phase, as opposed to really good deep physics understanding. So now let me go back to the climate record, or the TSI record here, the proxy-based one. And like I said, there are actually several of these. So if you really just took sunspots, things would be pretty flat in terms of solar minima coming straight back across here. But then there are other assumptions people make. Maybe when the sun had fewer sunspots, it was overall less active, and they've reduced some of the expected output based on the amplitude or the duration of solar cycles. Other ones are much more sophisticated, such as the red here and the new one that the IPCC is using, that rely on open flux, trying to understand, correlate the sunspot record with cosmogenic isotopes, all tied to the latest measurements that we have. And some of those are a little more physics-based, a little more solar physics-based, do show a bit of a decrease. Most of these models, though, show we're decreasing something on the order of 0.05% between now and Maunder minimum. Some are more extreme, getting up to almost 0.2% decrease, going back to Maunder minimum. The sun drives, it provides almost all the energy that comes into our Earth's climate system. It's about 2,500 times as much energy as the next source, which is radioactive decay and geothermal. You notice greenhouse gases really aren't a source of energy for the Earth. They kind of regulate what happens to the incoming light. But in terms of pure energy, the sun is providing 2,500 times as much as anything else. So a small change in the output of the sun for a long period of time would have an effect on climate. And luckily, the sun is fairly stable at these levels, which is good and bad. It's good in that it means we've got a nice, stable environment we live in. It's bad, or let's say interesting, in terms of if we want to be able to measure changes, it's difficult to do because the sun is so stable and changes so gradually. Here are several papers that have been published predicting or showing different estimates of how much lower in watts per square meter the sun was at the time of Maunder minimum. But you can see there is no really good, you might have started to think for a while, oh, we were coming to some good agreement here, but then there are a couple of, even recently, a couple of big sort of outliers in terms of estimates of how different the sun was during Maunder minimum from now. So a lot of variability still. And like I said, one of the bad things is these kind of climate measurements are very difficult. You can go out today, and if you want to measure climate, you can. If you want to measure temperature, that's a lot easier. You can go out today and you can take a measurement with your thermometer, and you can go out tomorrow and you can see a change, and your thermometer is probably consistent between today and tomorrow. But if you want to measure climate over 100 years or 400 years, you've got to have this one thermometer that doesn't change. You've got to observe it the same way every day for 400 years, and that's hard to do yourself. So you hand it to your brother, and he takes over for a while, and he might read it a little bit differently, or he might decide he's going to read earlier in the morning than you did. Climate measurements rely on good stability for the instrument and the observer over decades and centuries. They're much more difficult than the kind of space weather that you might have heard about this morning. Those are exciting events. Bang, right now, something exciting happens. Climate's a lot duller, perhaps, but very difficult. But long term, it can have big influences on us. But do want you to appreciate how difficult these measurements can be, because they're the things that could be affecting our long-term trends, and they're small. Take a couple of the extreme cases of what we think the sun was doing over the last 400 years, and I'm just going to focus on something as extreme as going into or out of Maunder minimum. If the sun were changing, such as it did, Kopp coming out of Maunder minimum. If it were doing that now, we'd like to be able to see that, especially with all the hubbub about the last solar cycle and how we're going into another Maunder minimum. It'd be really embarrassing if we couldn't measure it. So here's what it would take to measure the exit from Maunder minimum. And with a less extreme model and a more extreme model, it means you're looking at something on the order of a change in the sun's output of 0.1% over 80 or almost 100 years. Not an easy thing to measure. So a Maunder minimum variation is, like I said, on the order of 0.1% over 80 years or so. If you want to measure solar cycle variations, I've plotted up in here the 11-year solar cycle roughly. Those are big fluctuations on shorter periods of time. 0.1% changes over 5 years or so, relatively easy to measure. Rotational changes, 27 days, boy, it's easy to see changes on short time scales, but hard to see those changes in long time scales. That's what we need to be able to do. And to do that, you either need instruments that are incredibly stable and observing continually. So here, if you want to measure a Maunder minimum variation, you'd have one instrument or a series of instruments that would maintain stability by handing off measurements from one to the next. But they've got to be able to track things and be stable to better than 0.001% per year. And they've got to keep that up for a century. Another approach is to work with absolute accuracy. If you had an instrument that had an absolute accuracy or a net uncertainty that's small enough, you could go out today and take a measurement and say, I know the sun's value and the uncertainty on it is this small amount here. And then you could take an identical instrument 80 years in the future and fly it. And if there's a difference between those two that's outside of that small uncertainty you've associated with that instrument, you could say, that's due to the sun. It's not due to uncertainties in the instrument being so big that I couldn't tell a change over that time period. So if we make our absolute accuracies for doing radiometry better, we can also detect changes with different measurements without relying on continuity. And that's the approach that we're going after, is trying to improve the absolute accuracy of various instruments. The source total irradiance monitor, it improved over the kind of 1,000 part per million or 0.1% absolute accuracy of prior instruments. And we're trying to make things even better with future instruments. So working on absolute accuracy and very good stability to be able to see long-term changes in the sun's output. Here are actually all the different measurements that went into the composite that I cheated and put together earlier for you, where I plotted them all on my favorite scale down here. But what we really need to avoid these sort of differences between instruments is absolute accuracy that's much better, something on the order of 0.01%. And, like I said, a stability of 0.001% per year. And what those help with is avoiding differences between all these offsets on this scale here, and being able to see long-term changes as long as we're doing continuous measurements. So working towards each of those. Yeah, Joan.
The total radius, do you measure at the same wavelengths? Does it start to become important when you're getting that?
It does. You try to measure all the wavelengths. So the materials that we have, or the detectors we have, we do wonderful things with solid-state detectors, but boy, what a narrow wavelength range they work in. These are very crude by comparison, but wonderful in terms of the wavelengths that they'll absorb. So what we're using are black cavities, and these are conical cavities that are blackened on the inside, so the light comes in and is absorbed. All wavelengths of light are absorbed and heat up the cavity, and it's basically a temperature measurement, a bolometer, that we're using. And the black surfaces and the geometry of the cavity absorb light well up into the far infrared, and then all the way down into the soft X-rays, down to the point that energy will start to go through about 4 millimeters of the solid silver metal that's behind the black on the inside of the cavity. So they're crude detectors in terms of the simplicity of them, but wonderful in terms of the flatness spectrally that they have. and the wavelength coverage that they give us. So we do try to get everything. Maybe you'd say you don't worry about 100 microns because there's so little energy out there. That's much less than the 100 part per million absolute accuracy that we're trying for. But you really do need the visible extremely well, the near-infrared extremely well, and then a fairly good extension into the mid and far infrared, and a fairly good extension through the UV. So we did launch the, yeah.
So what is the gun software?
What's the what?
What is the gun? How big is the gun?
Oh, tiny. It's almost nothing. But we're collecting it anyway. Yeah. So it's on the order of a fraction of a part per million, especially with quiet sun. It can be a little bit higher when there is an extreme event. But even those extreme events, and I'll show you one later on, are so short-lived that they don't affect things long-term climate-wise. No, because the Earth is actually a lousy absorber. The Earth's albedo is 0.29, so it's reflecting. Yeah, what you really want to know is the total amount of energy we've got coming in, and then if you did have good spectral measurements of the energy coming in, then you could start to worry about exactly where that energy goes, how much of it's reflected from or absorbed high up in the atmosphere, which is real wavelength dependent. So you want the total amount of energy, but you would really, ideally, also like to know spectrally how much total energy is coming in everywhere so that you can start to figure out where it's going within the entire Earth system. So that would be ideal, but we're a long ways from being there yet. We're working on it, but not at this level of accuracy yet. So we did launch the Total Irradiance Monitor, a TSI instrument on source in 2003, and I'm going to go through some of the highlights from that mission. It was a 5-year mission, and much like the Starship Enterprise, it kept going for quite a while longer. It's been up almost 11 years now, although it did quit taking data recently. One of the things that we've done with this instrument is established a lower value for the TSI. Another one is this instrument has been more stable than anything else that's flown before. It's a sensitive instrument, more sensitive than anything that had flown before in TSI, and acquired the first flare measurement in TSI. And I'll show you some of that as well. And observed, just for fun, a couple of planetary transits, purely opportunistically. So here's our TSI climate data record, the Spaceborne one. And that, like I said, really came from a dozen different experiments. And you see immediately, they don't overlap. And it's not a case of, oh, why didn't you guys calibrate those before they went up? These are all calibrated instruments, but this was kind of the level of agreement that they had. This is 0.1%, this error bar right here. Radiometrically, that's doing reasonably well. We think we can do a lot better, and we need to do a lot better, so we're working on it. For a while, you could say, oh, that first instrument that went up wasn't calibrated too well. We're doing better. Oh, and these new ones, boy, we've really gotten things down now to where we understand what we're doing. And that was kind of the story when we launched Source with the new design and some good improvements. And it came out a whole bunch lower than anything else that was flown or had flown up to that point, and really confused things for a while. And one lesson learned from that is, when people kind of agreed here, they were all happy. They didn't look too hard at their instruments because they were agreeing with everybody else. Consistency is comforting, but it doesn't necessarily mean that you've got good accuracy. Fundamentally, the way these instruments work is they've got these black absorptive cavities. Incoming sunlight comes through a precision aperture and gets absorbed by that cavity, and you measure the temperature, and that tells you the entire amount of radiant energy you have coming in to the instrument. Ratio that by the very well-known area of these apertures, and you've got watts per square meter, or irradiance. You've effectively, very simply, taken the entire wonderful sun you guys are familiar with and condensed it into one number right there. You do have multiple cavities so that you can track degradation in a primary cavity that you're using all the time, but fundamentally, that's how all these instruments work. They do have a really slight design difference, though. George Lawrence, who's retired now from LASP, brilliant physicist and EE, had never built a radiometer like this before, so he kind of came at this with a fresh approach, didn't really look at how other instruments were designed, put a small precision aperture up here at the very entrance to the instrument, and the cavity deep inside. It turns out all the other instruments had the opposite geometry. Precision aperture was deep down inside the instrument. It lets you improve things like rejection for things that are outside the field of view, perhaps. But anyone who's tried to blacken the inside of a telescope and then shone sunlight on it knows how hard it is to get something completely black. These instruments are letting in 2 to 3 times the total amount of light that they ultimately want to collect through this aperture, and unless you've completely blocked all of that light, you can look at black surfaces that you've illuminated by the sun, and you can see them. They're kind of black. They're not as black as you might like. They scatter. There's enough scatter in here to be raising the value of energy that these instruments are reading, and it's an erroneous measurement. We've now done lab experiments on ground-based versions of these other flight radiometers and seen increases as we enlarge the sunlight, the beam that we have coming into the instruments, and they're kind of on the order of the offsets between the different instruments in the record. So this really is the main cause of all of the offsets we've had in the TSI record up to this point. So Akram, the group in green here from JPL that had been doing these measurements for over 30 years, has brought a version of their most recent instrument to a calibration facility that we've built here. And they, once they realized how much scatter they had, lowered their value. Another instrument, a Swiss instrument that was launched about 3 years ago, did these calibrations prior to launch. So they were the first instrument to really transfer the ground-based standard up to orbit, and again showed that, yes, indeed, this is really the value of the TSI. It's not as high as it was thought to be previously. So now we're again in a state where I could say, boy, yeah, look, we're doing well. We're all agreeing, and I've got to remind myself that consistency is comforting, but we're not done yet.
Looks like it's about 1% spread.
But total, yeah.
And your previous chart was showing 0.1, 0.2% changes. That's relative to changes in the aperture.
Let's see. They're up to 0.5%.
Okay, that one's 0.5.
Yeah. So some of them are a fair amount larger. Other ones we'd found some optical or power problems with. But yeah, a lot of it is scatter. No, this isn't all of it. But this was a good demonstration that, boy, the uncertainty on scatter, even being able to take...
I remember George giving a seminar years ago, and he was talking about how do you get the size of the aperture going to a lens. So you take an 8-inch drill and
That wouldn't do it.
sort of thing,
No. So that, to be able to work at the kind of 0.01% that we'd really like to, that aperture is more than hand drilled. It's diamond turned by fancy machine shops with fancy coatings, and then it's sent off to NIST and calibrated down to 25 parts per million. And even then, you end up having to take wonderful physics things, diffraction, and correct for diffraction of light going through that aperture. So,
things in the error budget.
yeah.
Uncertainty in the size of the hole.
Yep. Yeah, and even bigger than the uncertainty in the size is the knowledge of the diffraction. The diffraction for us is a 450 part per million effect. Diffraction is something that you know from physics very well, but NIST, who does these calculations and characterizations of diffraction, will only quote a 10% uncertainty on those diffraction calculations. So 10% of that 450 parts per million is even larger than the uncertainty in the aperture area itself. But that's one of the biggest contributions to the uncertainty budget. So yeah, another rule that George had was when you make something 10 times better, you have 10 squared more things you have to worry about. And it's pretty much true. You improve one thing, you try to improve one thing, and you end up having to make a whole bunch of corrections and then uncertainties on those corrections all along the way. So that's what keeps this fascinating. So we're now again in a state perhaps where we could say, oh, have we solved the entire problem? But we should take that and blow it up and keep pursuing. Why aren't things in better agreement than this now? So still working on it, and things are still exciting because of that. This isn't the first time that something that we might call a constant. You remember people used to call TSI the solar constant, which is a real misnomer. It definitely does change, but over time, and this only goes up to about 1975, several constants have changed with time. And you notice in each case, a lot of these are monotonic, but in each case, where we've ultimately ended up with these physical constants is well outside the uncertainties that were attributed to that constant much earlier on. So another lesson learned is experimentalists are optimists, which is probably why we keep playing with things. It's real nice to have 3 different instruments up, 4 now, simultaneously taking data, because you can compare them. So here's the time. This is kind of coming out of solar maximum, going through solar minimum in 2008, and then heading back up into solar maximum again, or solar half maximum as it's turning out. But if we were to take just the solar minimum period and compare the instruments at the same time there, that's a time when the sun was pretty quiet. So if I just blow up that short region near solar minimum for the total irradiance monitor, the Acrim 3, which was observing then, and the Virgo instrument, which was observing then, this is what I see. So for the TIM at least, we've got some fluctuations through here, and some of that is, probably most of that is real solar fluctuations. The sun's never dead quiet. Standard deviation of all those data is 17 parts per million. And that's a combination of both solar variability and instrument noise. And you can't distinguish one from the other. But then you can look at what the other instruments are doing. And they're observing the same sun at the same time. So the differences between the different instruments are instrumental. This is a neat way of being able to track down differences between each of these various instruments. And you can see there are some artifacts. There's a definite oscillation in these data here that isn't in the other instruments. It's not common mode. There's a spike here in the Virgo data and another one 90 days earlier. And Leif Spelsgaard looked at that and says, oh, that happens every 90 days. I know what SOHO does every 90 days. It does this keyhole maneuver. And sure enough, these artifacts are tied to maneuvers of the spacecraft. But they're things that stand out because we have more than one instrument looking at the same sun at the same time. So you can start to see artifacts in the instrument by comparing them. And then just relative to TIM, there is no reference standard up on orbit. So I've got to pick one of the instruments as a reference. Compare Virgo to TIM, Acrim 3 to TIM, and you see long-term changes in each of those, but by different amounts, different slopes. You also, again, see these oscillations in the Acrim data, and they change in periodicity with time. So again, it gives us a good idea of what we need to be critical of instrument-wise. Some of the newer instruments, the Primos instrument that was launched by the Swiss about 3 years ago, agrees much better with the total irradiance monitor data that we have. But in any case, it's very useful to have multiple data sets. So you can say, okay, I can track changes between instruments with time. how well can we really track long-term changes? What if I take those residuals and I start to smooth them by different amounts? Again, these are just residuals relative to a kind of arbitrarily chosen TIM in my case, but it could be any of these instruments. But when the instruments aren't all showing the same trends relative to each other, that tells us we have instrument artifacts that we need to get rid of. So here are 1 year smooth residuals. If I want to really see how well we can track things with time, or how stable the instruments are, I can compare one to another, and then I can look for, if things were really constant, if one instrument varied nice and linearly relative to another, you could say, oh, that's a linear trend, I can take that out. But you can see on here that it's not a nice linear trend, and you can't really take it out. If you look at variations in the slope of this, the variations in the slope give you an idea of the uncertainties of these instruments in their stabilities. And they're much bigger than the 10 parts per million per year that we'd really like to be able to get to. So we're not there yet. We're not able to really say, yeah, we've nailed it. We've gotten all these instruments stable enough to see long-term changes in the sun's output like we would possibly have coming out of Maunder minimum. At least not all the instruments are there yet. If you smooth things with time, they get better and better, but they're not down. This is 100 parts per million per year right here. They're a little better than 100 parts per million, but they're definitely not down at the 10 parts per million per year level that we would like them to be. So we do need to improve some of the uncertainties. What does that mean when you put together, with all these dozen different experiments, you put together one composite? Well, we've never put together one composite. It's sort of like the climate data record. There are several data records. So here are the 3 most common composites, and you can see that there are differences between them. One of the more common ones, by Klaus Frohlich, has the sun coming back to about the same level at solar minimum between these 2 minima, and then a slightly lower level for the 2008 minimum. Dick Wilson, with his ACRM data, shows an increase, a substantial increase in the solar minimum value back in 1996, and then a decrease for the newer one. How big a difference is that? If I plot on here, these triangles, what I've done is I've said, let's say I know the value of the solar minimum right here, and then I'm going to come 11 years later and measure the value of the next solar minimum. But my instrument uncertainty, ideally, would be down around 10 parts per million per year. Well, that's the size of this uncertainty budget right here, this error bar right here. That triangle is kind of the increasing uncertainties with time in your measurement. And we really can't measure differences minimum to minimum like we'd like to be able to. You'll perhaps read papers that say, oh, we know things are lower now than they were before, but they're really not that far outside of any uncertainty of the instrument measurement itself. Yeah?
You know, I mean, to my eye, the biggest difference between those that you've alluded is the, 6 parts per thousand offset between the sort of zero limits.
Right. That is the absolute value here.
Yeah, so what, I mean, in terms of global climate, what kind of an impact does that level of radiation difference have? Okay, good.
No, it actually does.
No, it has no impact at all, because you're talking about a 1% difference in total, the baseline.
Is that a degree Kelvin?
Yeah, but there's
I guess it's the changes.
That's what the climate people...
absolute change of 1% climate model is clearly the noise compared to all the other tuning factors that go in climate.
That's what we originally thought.
Tuning on the order of 10, 20, 30, 40%. All of the radiant transits affected personal radiation.
So that was kind of the way I thought this would probably go originally, was that the baseline doesn't make any difference. But David Rind has been working on this with some of his climate models more recently, and just talked to him and Judith a bit at the AGU meeting, and it's a little more subtle than that, because what the climate modelers do, they don't know the total amount of outgoing energy. That's got bigger uncertainties on it than the incoming energy. So what they do is they take a value for the incoming energy, and then they have to balance that by putting in appropriate clouds to be able to make sure they're reflecting enough light to come up with some temperature, global temperature that matches what we really see. But they can't control the clouds everywhere. The clouds they can control more around the troposphere. So having a lower overall value means that they've got to adjust the number of clouds that they have, and they can only do that regionally. And so it does actually regionally affect things differently, even in the climate models. It's not just a scaling factor for everything. It complicates things regionally. So that was a subtlety that I hadn't appreciated enough. So they are starting to use the lower value, but it is also tweaking things regionally differently from how you might just think of offsetting everything simplistically.
Effective parameterizations applying those cloud-generated models.
Right.
That are efficient.
Right. But if they're going to come up with some sort of global climate model that's kind of representative of what we have, they've got to adjust things differently.
Effective parameterization.
Yep.
10 million other.
Yep. So it does have those kind of effects on the climate models.
Right, it makes it forces you to reach
Right. Yep. Yeah. So it's a bigger effect than I actually thought it was going to be in the energy balance. But the other reason we want to improve the knowledge of the incoming energy is eventually we're going to have good measurements of the outgoing energy. And we don't want to be the limiting factor when they get those outgoing measurements to be a whole bunch better than they are right now. So there are differences between these composites, and if you're if you're a user of these data, you look at these three and go, well, heck, if the people in the community can't agree, how am I supposed to choose between them? And we have put together an International Space Studies Institute team that includes all of the people who've worked on these different composites to try to come to some agreement, produce one composite for the user community to be able to have. And even if we can't come to some absolute agreement, we're going to attach time-dependent uncertainties to this composite so that people using the data have got a good understanding of where they can trust the data, or where they can trust the composite and where they can't, because that's lacking now. Yeah, Martin. I don't know. Right. Since that goes as t to the fourth, it's so it's degrees, but yeah.
Our ability to measure the effective temperature of another star is, in other words, so much more limited by a whole lot of other things. And so, having a super accurate value of the sun is complicated, but in practice, it really doesn't make a difference.
Probably, if it were a true gray body or true black body, maybe we'd be down at a level where it would help, but I suspect there's a lot more unknowns in the structure through the atmosphere and the different regions contributing different temperatures that mess things up a lot more.
It's just hard to measure on stars. Certain parts of the spectrum can be important. Early type stars, the whole region in the Lyman alpha, below the Lyman continuum edge, is inaccessible to the stellar station. And so we don't know really what the energy distribution of those objects are using some models. But it's good to have, it's very comfortable to have an accurate value of the sun.
As long as we're not complacent with that comfort. Yeah. So we're working on improving composites, and it does make a difference. Which composite you choose has led to some very wild, I'd like to say speculations, but the sort of things that climate deniers like to jump on and say, oh, it's all due to the sun, and it can have a big impact on politics and policy that can be a real nuisance. Let me skip over a couple of slides showing stabilities of instruments and jump ahead to something that gets a little more exciting. So, with source, we've looked at a lot of different wavelengths as well. So here was October 2003, big, huge sunspot group that came across, a couple of groups that came across the disk. And right here was an X17 flare. I think at the time it might have been the third largest flare, and a couple of weeks later it became the fourth largest instead flare to be observed since GOES has been up. But we break those down spectrally. We get measurements at lots of different wavelengths. But what was neat about this was that we got, in red here, are the TSI measurements, where you can see the flare right there. The sun's moving around at kind of this 50 part per million level all the time. But this was a jump of 270 parts per million that stood out enough that I took the plot and went down the hall and said, what happened right exactly here? This is the first measurement that anyone had had in TSI of a flare. And because it's TSI, we're integrating the entire spectrum. Flares stand out a lot when you're looking at ultraviolet X-rays because the sun is so dark and there's a lot of energy that's put out from a localized region. But in TSI, it's tiny, 0.03% or so, and it only lasts for a short while. But still, the first measurement we've had. But you can spectrally, well, what TSI does is it spectrally integrated the energy. So we know the total amount of energy from that flare radiantly, and have done that for several other flares too. And Tom Woods put together a nice paper showing some of the results of how much energy comes out in the visible in the near infrared versus how much comes out in the ultraviolet. A fair amount more, about 50% of the energy seems to be coming out in the visible and the near infrared. A bit more than we'd thought previously. Also did get to look at a couple of transits, planetary transits, just because we lucked out and launched at a time when we had 2 Venus transits coming up. Venus is easy to see. It's like a small-sized sunspot. Here in red are the normal fluctuations of the sun, and then here is the Venus transit. Fitted to a kind of pink curve that's faint to see on here that includes limb darkening and the position of the planet, the spacecraft, but does show that we really are measuring just what you'd expect to see. And here is Venus. Whoops. So that little spike right there for 6 hours was Venus. Looks just like a little sunspot that came and went pretty quickly. Here's Mercury. Can anyone tell me we have 2 Mercury transits? But boy, that one's hard to see. Remember, the sun's moving around. These red dots are solar measurements. So here's 8-hour time span. Each of these, I'm sorry, it's much more than that. That's more like a day. But the red dots are the normal fluctuations the sun's going through, and they're in the order of 100 parts per million. And somewhere here in the middle is where Mercury went across the sun, and again up here. But it's only a 30 or 40 part per million effect. Small. It's not something you'd ever look at these data and say, aha, there it is. But that's exactly what we want to be able to do if we want to see planets going across other stars. So let's look at how likely that is. Here's a couple of years of total irradiance. Let's take a couple of months of that and blow it up. This is what the sun looks like moving around over a couple of months. There's our 27-day periodicity with activities. Now let's take 2 weeks, 14 days here, and blow that up. And this is what it looks like. And remember this, because in a couple of minutes we're going to come back to this. So there's our data for 2 weeks with the sun. Yeah.
Is that all basically just solar noise?
Uh-huh. Yeah. No, this is solar noise, solar signal, I like to think of it as. But it really is real solar variability. It's not instrument noise. It's oscillations in convection mostly that causes this. So the low frequency stuff is 27-day activity that's rotating around and varying. The high-frequency stuff is a combination of convection and oscillations integrated. So it's 50-second cadence is what I'm showing for these data here. So here's one day. Let's take that one day and blow it up. And we have different orbits where we're occulted. The spacings in here where we're occulted, blocked by the Earth. So here's the sun moving around at 50 parts per million all the time. Take a couple of orbits of that and blow that up. And there's how much the sun's moving all the time. And it's convection, oscillations. So remember, it's moving around at 50 to 100 parts per million all the time. Now, if you're going to have something like the Earth go across the sun, and you're going to view this from another solar system, what's it like? Well, if the Earth goes right across the center of the sun, this is a limb-darkened plot here, darkness plot that you would see, you'd see a change of about 100 parts per million. If it goes through a chord, maybe it's last 60 parts per million. The Earth would be something like an 80 part per million dip in the signal on top of this star that's moving around at 50 to 100 parts per million all the time, and you want to be able to see that. Can you really do that? And the answer, luckily, is you probably can. So I've simulated Earth-type transit across the Sun-type star right here, and it does sort of stand out. And now I'm going to come back to that plot I told you to remember, and you'd look at that now and go, yeah, there it is. And the reason you see it is that the sun is moving around at high frequencies, at 50 to 100 parts per million, and at low frequencies, but it's not moving around at these kind of characteristic 8 to 15 hour transit time scales. So indeed, Kepler would work if it were launched, and at the time it hadn't been, and since then it's proven that yes, indeed, it really does work. So we're still trying to get continual measurements of TSI. We had Glory that was supposed to be going up after Source, and it failed on launch, which meant that we had a potential data gap in these measurements coming up. And we luckily recently have plugged or filled that with TCTE. This was a real quick turnaround mission designed to continue our total irradiance monitor measurements after Source and before TSIS goes up in 2017. And a fun experiment to work on because it was real short time frame. We didn't have a lot of time to get a replacement up for Glory. And NASA and NOAA let us put this instrument together, put it on a Ball spacecraft along with a few other Air Force instruments. This is an Air Force-led mission, and they are wonderful to work with. They really stick to nice time schedules. But Ball built the bus. Here's our instrument, the total irradiance monitor that's on here. We did launch this on the 19th of November, just over a month ago. And it's going to be continuing the TSI measurements after Source. Like I said, Source would quit taking data the end of July. We're going to be turning it on again for a couple of weeks, or probably less than that, the end of this month, to try to overlap with the TCTE that's recently launched. Aiming to get down around 0.035% absolute accuracy and 0.01% per year stability with this instrument, and have done good ground calibrations of it ahead of time. Right now, what it will be doing, since it's not the primary reason for flying this mission, is it'll just be getting one orbit per day of solar measurements. But at least that'll be enough to hopefully overlap a little bit with Source and then continue into the near future at least. It's only a 1.5-year lifetime mission, and only reason to do it will be if it lasts a fair amount longer than that. We have just completed commissioning activities, and as of yesterday, we started taking TSI measurements, and do have this campaign coming up the end of this month where we want to power Source back on at a time when we think we can. I know everyone wants to know what's the value that we're measuring, and having just started yesterday, check back with me in a couple of months, perhaps at Boulder Solar Day, and I'd like to have an answer by then. So where are we now? Quality measurements, you really need 10 parts per million per year stability if these are going to be good climate measurements. And we're just getting there, we think, with the newer instruments. We need to be, and we have improved absolute accuracies a lot. We've figured out why there are such big discrepancies on the instruments that had been measuring up to this point. But so far, nothing has really launched that says, yes, indeed, it's a 100 part per million instrument. We're trying to do that with the upcoming TSIS instrument that we've now built and are waiting to launch in 2017. But so far, it's instrument stability and measurement continuity that are needed to really be able to see long-term changes at the level that climate scientists need from the solar measurements. We are working on improving the composite for people who use these data. A couple of things we have learned from source. We've learned and established this lower irradiance value of about 260.5 watts per square meter, or 1,360 watts per square meter, representative of solar minimum. Learned that a lot of flare energy is released in the visible and the near infrared, and had the first measurements of that net energy. Did decide that, yeah, you could probably see Earth-type planet transits, and now we've got a couple of thousand of examples of, yes, that really is the case, thanks to Kepler. TSI climate data record is getting down to the accuracies and stabilities that we'd really like. It's, be neat if we'd been able to start that 35 years ago, but we're getting closer to it. And we do have TCTE now up to be able to continue these measurements into the future. The next thing we're going to need, like you alluded to a little bit, Tom, is if we knew the outgoing that well. So starting to work on that a little bit too, but that's a whole nother talk. So thanks, everyone.
Thank you, Greg. Questions or more questions?
I'm just wondering, when you are trying to get to such high accuracy, is there any significant absorption or scattering from, Earth's atmosphere between the satellite and the sun, like absorption by the geocorona or?
Not at the part per million level. So we're up at 600 kilometers, well up enough that we've got very little satellite drag. So there really isn't much out there that, the biggest effect would be slowing the satellite down with time. But in terms of absorption, no, that there really isn't anything that's significant affecting total amount of energy that we're seeing. A lot of bigger effects like thermal changes and things in the instrument that you have to worry about, but not additional absorption. But that is really what drives you to have to be up in space to get these measurements. But there's not a heck of a lot of energy in the EUV to start with, and not at 600 kilometers. There isn't much.
It's not going to affect TSI.
Right.
So I guess, let's see, Scott McIntosh, he was showing me the Virgo Soho, right?
Right.
Right. So he's showing me the long-term Virgo record the other day, and his claim was that the 100 parts per million decline over
11 years or so,
from minimum
yeah.
to minimum that they claim is rock solid. And I said, well, talk to the TSI experts. There's a lot of controversy in that field. What do you think?
Yes, I don't think that it's rock solid. Klaus Froelich does. But even when he's gone through his paper, it's a kind of 1.4 sigma measurement. So if you start looking at all the uncertainties of the data that he's had to use in the corrections over that time, it's maybe a 1.4 sigma measurement. So not something I would say is rock solid.
Bigger numbers. But then other analyses are coming up with 0 or even inverse.
Right. So no, it's definitely not rock solid. The instrument uncertainties are as big as the changes that we see over solar cycle timescales for the previous instruments. We like to think that what we're starting with now is doing a lot better. And I really wish we'd had the source TIM going from one solar minimum to the next, because it's by far the most stable instrument up there. let me briefly show you some of the Virgo degradation. So here are the 4 channels on Virgo, and this pinkish one here is the primary channel. So initially, when it launched, it immediately increased in sensitivity. It didn't decrease by about 600 parts per million, just over a few weeks. And since then, it's degraded by about 4,000 parts per million, 0.4%. And you've got to be able to see a change of 100 parts per million that's corrected from one solar minimum to the next in something that's degraded by that much. The more something's degraded, the bigger the correction you're applying to it, the bigger the uncertainty associated with that correction. It's hard to believe that you really have gotten 10 parts per million per year stability knowledge of this huge degradation. We've got this instrument uses a black paint as its absorbing surface. And black paints are hydrocarbons. You expose them to ultraviolet, and they degrade. So this isn't surprising. You have to correct for this on orbit. What we've done with the total irradiance monitor is we're using a nickel phosphorus, which is an etched metal. So it's not a black paint. It's much more robust. The degradation that we've seen in the 11 years we've been on orbit is 200 parts per million. So a 20th of what Virgo has had. And unlike the Virgo, which kind of went up and then has gone down, or unlike these other instruments that really aren't following any specific pattern, ours is very close to following what a first-year physics student would say, oh yeah, it's going to degrade like an exponential. So the blue line is an exponential fit to this. So it's...
But can you tie this to your new vision?
The ones from TCTE, if we get this good overlap period, the end of this month, with stable instrument, with both instruments being stable, then we can transfer things. So that's the intent with this campaign period we have coming up. It would be nicer to have a half a year of overlap, but the source batteries aren't going to do well enough to let us get that. So no, we're going to lose a fair amount doing this handoff. And actually, we may have lost a fair amount already because the source instruments have been off since the end of July. We haven't been able to track their degradation since then. So we may have lost that stability already, but we'll see when we turn it back on.
You have the Swiss.
We have the Swiss, but then you're relying on an instrument that's not as stable to fill this 6-month gap. So you have something that's not achieving 10 parts per million per year that you're going to fill a 6-month gap with. You can also, for short periods of time, you might get away with relying on proxy models of solar activity. That they're not good long term, but they may be able to fill in intervening changes in activity for this last 6-month period. So I'm certainly going to look at everything that we've got. I'll look at Virgo, I'll look at the Swiss instrument, I'll look at models, and we'll look at the direct source to TCTE comparison that we get. But really to say that we're going to be able to tie together source from the end of July to TCTE now is going to take a lot of work before anyone should believe me if I say that we've tied them together to 10 parts per million per year. So I'm looking forward to a neat challenge coming up here trying to do exactly that. But I don't know how well it'll work yet. Phil.
Has anybody tried to tie the variations that you saw, the high frequency variations that you saw to measurements from SDO?
Not SDO, but Gong. Jack Harvey some time ago did a neat little project at one of the, I think it was an SPD meeting where he had a poster where he'd taken Gong measurements and tried to spatially integrate everything that they had for, they don't measure irradiances, they measure velocities, but they also get some intensities. But he tried to correlate the velocity changes that they were seeing spatially integrated. and could do a reasonable job of it for short periods of time. So it was enough to be intriguing. That, yeah, a lot of it. Just shown as a presentation. I don't know that he ever published it. He
Talk to me later.
looking for another paper. Yeah. Yeah, no, I don't know if he ever took that far enough to publish it. He may have. But it was kind of enough to say, oh yeah, that's suggestive. Yeah, it really does look similar to the oscillations, but not a perfect match or anything. So.
Good. No more questions. Let's thank Greg again.
Oh, thank you.